Hello everyone and welcome back for more FumeFX tutorials. This time is going to be about the Flamethrower, and all you need is the 3D Studio Max and FumeFX. First, make sure that you're using centimeters for this tutorial, and for time scale I'm using NTSC, which is 29.97 frames per second. As you can see, this time I have everything set up, and I'll focus more on what each parameter does and the influence on the simulation. So for start, you see we have a Flamethrower guy here, and I have created the two emitters. One is for rendering and one is for the simulation. The render one is going to create particles from these selected faces and is going to be used for rendering only, while other emitter is for the simulation. It also has face selected for the emission, and this one we're going to use to emit particles for the FumeFX simulation. It's a little bit wider as we need a bit more thickness to the fire stream, so you can directly control the shape of the fire by using those particles that are separated from the ones that are going to render. Okay, so I'll start with the rendering particles. As you can see, we have three groups here: source for render, source for simulation, and later we're going to create some drops from the Flamethrower stream. Generator of surface, generate particles from the frame 0 to frame 150 to the source render particle group, and we're going to emit from the emitter for render object. And I uncheck the animated mesh because this shape is animated and it can save us a little bit more time, especially on complex meshes. Emission is from the face, any face that's selected, and we generate about 200 particles each frame. And here I'm using the surface offset, and you'll see why, because those particles are very fast. By using the surface offset, we can create this stream as continuous. However, since this stream is very fast, we can also go to the simulation and increase simulation steps to 3, and this is going to create a much tighter pack of particles as well. But let's go back here and let's adjust this surface offset. Okay, we can use something like 30 so that particles form one continuous stream, and as you can see, they're shooting away from the emitter. And now I'm going to create another particle system that is going to be generated on the larger source we have here. Those are particles that will be used for the simulation, and they are colored red, so I can go back here and we can go to these particles, and I'll leave this surface offset a little bit shorter. It doesn't matter, as we're going to emit anyway from some area that's a little bit further from the nozzle itself, as initially this napalm mix doesn't burn until it moves from the emitter some about 1 or 2 meters. Okay, so those are two emitters. This has similar properties: phase random, selected using offset. Lifespan doesn't matter here, and one important thing here is that the speed of the particles is 3000 units per second, which means right now we have centimeters, that will be 30 meters per second, as our frame rate is 30 frames, which means this will be 30 meters in 1 second. Okay, for this sim source, you can control independently from the render one the spread. So you see, you can spread this as you like, independently from what we're going to render, as we want this rendering stream to be pretty tight, so we see a liquid stream as it is. So now we have those two particle systems set. There's one more thing that we need to do, is to add gravity and to add some lifespan. Now for gravity, just disable this one. Gravity I've set something like 20 units in negative z direction, and I'm going to use particle travel distance, compare, that's, as we said, 13 meters, and in this case I'm going to delete particles that have traveled above 13 meters to this point. So whatever you do, if you decide to change particle velocity or any other property, it's important to have this initial stream that's 13 meters long. Now the next thing that I want to do here is to show you that this get particle group here uses regular expressions, which means that with one expression we're affecting both sources here, the sim source and render source. Regular expressions are very powerful. They allow you to procedurally add any particle source, for example, that begins with the SRC letters, to the get particle group node. However, you can also type in individual particle groups, and the system will get only those groups, regardless if there are any other particle groups that begins with the SRC letters. Okay, the next thing I'm going to add here, particles that are going to detach from the main flow, and they're going to drop in the ground, and they'll burn as well. So here I'll just use one simple version. So I get the same particles here. We can hide these emitters. Same particle, and what I do here, I get one random number between 0 and 100,000, and I compare the random value to be lower than 3, and in that case I'm spawning particle at the position of the original particle, and I add some short lifespan, about 1 second, and add some direction variation, and using the original particle velocity as the spawn direction. As you can see here, we get a particle. Let's just hide those particles. We get those green particles are spawned as particle is created, but I want those dropped particles to be created anywhere in the stream. And why is this going to be just when at the nozzle? Because each particle that's generated here, it has something that we call a seed. That's the render number generator seed. So in each case, this particle is going to generate the same random number, and this condition will be satisfied as soon as the particle is generated, which means as soon as it is generated, is going to spawn particle, and we're going to delete parent particle right away. So how can we add some more randomization here so that one particle can be activated and converted into drops at any frame? We need to change this seed number, so each particle will have a little bit different seed number on each frame, so it's actually generating a different random number on each frame. And now if we move the time slider, we can see that the particle is spawned here somewhere at 1/3 of the stream, and this process will now can happen at any position within the stream. Okay, so that's for the spawning particles, and now we need to add something for the drops, gravity, and a little bit of drag. So as they are generated, I wanted to separate from the main flow and to fall at the bottom of this grid. Now I'll unhide particles here. Okay, now here I'm using a simple shape for the render particles. It's just some tetrahedron, a small tetrahedron. For simulation particles we just don't need this simple shape, so we can delete it. And now I want those drop particles to collide. What I have here is I want to hide this big sand, a collider plane, so they stay on the top of this ground plane. So I have created another tab here, named it PhysX. First thing, you need to add PhysX solver, and for PhysX static collision, pick this ground collision object here. This ground collision is static, and we use mesh increase the static and dynamic friction, and as we don't want those drops to slide across the surface. And it's simulation group 0, and it's going to collide with simulation group 1, which are going to be our drop particles here. So drop particles are connected to PhysX object, which is now sim group 1, and they are going to collide with the sim group 0, which is the static collision. It's going to be dynamic object, type of sphere, and the radius of 1, also 0 bounce, and static and dynamic friction set to 10. Position iteration 4, let's move this to 10 and 5, and don't forget to lock the angle on X, Y, and Z axis. Now if we move the time slider here, we can see those particles collide with the plane and they stick on the plane. That's what we want for these particles set up here. Now since everything is set up here, I'm going to go to caching. You change your path and you hit the export button to cache all the particles here. So we use cache particles, and now I can disable those two tabs, and I can enable FumeFX and render a tab where I have the simulation info node that provides workspace path to load particle cache path. And since I'm going to render 130 frames for this simulation, I'm going to only load first 100 frames. We simulated for 130, but I load just 100 frames for the simulation. I use interpolate subframes that may be used for the motion blur, and other parameters as they were initially set. And next we get the FumeFX simulation reference. So whenever you're simulating with FumeFX, make sure that you have FumeFX simulation reference. Pick the FumeFX grid from the scene, and then use this grid for the sources and collision objects. Now for the particle group, the sim particles, I get those particles, and I want them to emit smoke only when the particle is away 500 meters from the emitter. So when particle passes 5 meter mark, is going to emit smoke, and we're going to emit fire when it exceeds 2 meters distance from this emission object. For the grid sources, I'm going to use particles. So each this particle will be a little sphere with a radius of 2, and the smoke type is set value 1, controlled emission by this compare operator. Similar goes for the fire, and all those particles here are going to emit temperature 100 degrees. They're going to emit all the time from those particles that do not emit smoke or fire to the last particle that emits and fire and smoke. And now the particles will introduce some pressure to the grid. So each particle here, source particle, is going to add some pressure. This pressure is going to add some volume to those particles and some velocities that go outward from this particle stream, so we get a thicker fire as those particles move away from the source. And for the velocities we use motion velocity of 1, which means that particles will inherit their velocities and pass them to the simulation grid. Next we have those drop particles. They are also grid sources, but since there are fewer particles, I'm using a larger radius of 4 and enable fire and temperature. However, smoke emission is disabled, as I'm going to set up this through the FumeFX simulation, as it's going to create smoke when the fire burns, and motion velocity scale factor is 1. Now we're ready to go for the FumeFX grid simulation. As a reference for the Flamethrower, I was looking at this video. They're using a military M9 Flamethrower. As you can see, at the beginning you just see the napalm stream without any fire or ignition. Later on, as the fire ignites, it burns, but it doesn't create any smoke. And later on, when the fuel is burned to some extent, you see smoke appears, and it has really nice reddish colors here. So I've used this as a template for the simulation and shading. It's really nice billowing smoke. And don't miss this top view when you can see actual length and how the smoke expands as it rises up. So we're going to recreate this behavior. So now about the FumeFX setup. The grid is very large, as you can see, as the grid spacing is only 1.5 centimeter. The grid height was not so tough to determine how high it should be. I've set it so that height covers the field of view, so if there's any smoke that's gonna hit the top of the grid, we're not going to see it. And the width of the grid is set from an experiment from the previous simulation runs. However, the width is set initially pretty large, but as we have high velocities here, we can expect that smoke is going to expand beyond this edge. So I have set boundless grid on the positive X side, so adaptive grid can expand here as much as it takes. So now I'm going to open up the FumeFX user interface so you can check the parameters that were changed. The parameter check gives you comparison between default and current value. So you can see the grid spacing is 1.5 centimeter, which defines a pretty large grid that can take up about 20 gigabytes of memory. But as you can see, I've set the positive X side as boundless, so I can expand further as it needs, and the memory consumption of course is going to rise to about 20-25 gigs for the simulation. Now you can see that it's adaptive grid and allow shrinking is disabled, which means that grid, once it expands, it won't be allowed to shrink again. So I added an extra padding, which means that the adaptive grid that's created tightly around the smoke, fire, temperature channels is going to have extra 20 voxels around. That's because extra voxels are not just empty voxels, they contain velocity, and velocities are very important for creating a natural rolling motion for the smoke and fire. So that's something I've said here. And sensitivities for all fields, as I said, smoke, fire, temperature. Simulation range is from 10 to 130 frames, and during the caching we'll minimize the grid, so the grid will be as tight as possible around the smoke and other channels that we simulate, but I added some padding for the motion blur. Now under the simulation tab I've increased the solver quality to 6 because we have really fast moving particles and high velocities within the grid, and thus I've increased the number of maximum simulation steps. Now, but the simulation steps, usually bigger doesn't mean better, because with more sub simulation steps you probably get more diffused smoke, as during each step all the fields need to be interpolated and moved along the grid by the velocities. And now the simulation uses velocity damping, which I usually avoid, but this time it was necessary to reduce the horizontal motion and to increase the vertical motion by using the temperature buoyancy, and also use smoke buoyancy to increase the vertical motion compared to the horizontal motion. That's now where we get to the fuel. I've set fuel buoyancy to 0 and decreased ignition temperature, so wherever there is temperature all the fuel is going to burn all the time, and the burn rate is decreased to 8, so we get long burn, longer flames, fireballs and stuff like that. I set heat production to 0, which means all the heat that's generated from the particle source will be the only heat within the grid. And the expansion, I've increased the expansion so that as the fire burns we get more expansion around the particles, and especially we'll get the expansion on the smoke as it rises. As you've seen in the reference video, there's a big billowing, expanding smoke as it rises from the ground. And a few things I'll have to explain here. I've used the positive and very large smoke buoyancy so that the smoke itself will rise even if there is no high temperature, because we have the velocity damping, so I wanted to prevent any smoke as much as possible that is going probably to stand still because of the velocity damping. I've set temperature dissipation strength to 0 because I don't want any temperature dissipation for this simulation. And now if we go and simulate this setup, it's going to take about 2 hours depending on your configuration, and you'll get nice flamethrower with lots of detail that now just waits for the shading and rendering part. For rendering I will be using Arnold renderer. Just make sure that from the FumeFX rendering tab you choose shader Arnold redshift volume, and that you export smoke, fire and temperature channels and velocity if you simulate the velocity and want to render motion blur. You can of course use a redshift render as well, and the workflow is about the same. So for the rendering I have this Arnold spotlight that illuminates the smoke and just a little bit around ground area, and I'm using the color, a little bit bluish color, 1 sample and 2 volume samples, of course atmospheric shadows, and this is the intensity exposure settings. And for the under rendering sampling, that's very important if you want to get proper volume rendering, using the ray depth of 2 for the scene and volume indirect 5. So this ray depth is very important, as if you use ray depth 0 there is no light bounces within the smoke, so you get just smoke and fire channel and no light scattering. Ray depth 1 means one bounce of the GI within the smoke, and this also has a great impact on rendering time. So basically in this scene the speed difference between ray depth of 1 and ray depth of 3 is that ray depth 3 will render as twice as slow as the ray depth 1. As you can see at these images, ray depth 1 or 2 is probably maximum for this scene that you should be using, and these samples are to remove the noise from the ground I have here, and for any noise that remains I'm using the noise. You can use optics or whatever denoiser you use for the imagers. And that's pretty much for this tutorial. Thank you for watching, and see you soon with the next FumeFX tutorial.